Hi, my name is Dave Morgan, and this is the presentation to accompany the poster on paper and pencil general relativity, and cosmology activities. All of the activities in this presentation were developed for introductory astronomy course at the college level, but I've also used most of them at the high school level for electives in astronomy and electives in Einstein's theories of relativity. You'll often see non-Euclidean geometry introduced by analogy of doing geometry on the surface of a curved surface like a sphere. So when I have my students first try to understand this idea, we do it by actually doing some geometry on curved surfaces, starting with spheres. I'll use yoga balls or play balls that I get from the thrift store, from the department store, and draw large triangles on these. And what students can see is that the usual rules of Euclidean geometry do not apply, that the angles of a triangle, for example, do not add up to 180 degrees, and that the circumference of a sphere is not equal to 2 pi r, or if you want to phrase it differently, that if you calculate pi using a circle drawn on a ball, you get a different value than 3.14. You can examine how these things depend on the size of the sphere by doing it on a ball of variable radius. I use punch balloons and blow them up and have the students measure the properties of triangles on the balloon, usually starting with the largest size and then having them gradually take air out of the balloon. They can measure the radius with a curved ruler. A good source of curved rulers is if you're near an IKEA. They always have paper centimeter rulers that you can use to measure the furniture. I always sneak off with 3 or 4 extras so that I can use them in my class. Anyway, in a slightly more advanced version of this activity, you can have students actually graph, say, the excess of the angles over 180 degrees as a function of the radius of the ball, or the obtained value of pi as a function of the radius of the ball. If you want to look at negative curved surfaces, it's a little bit harder to come across a good hyperboloid. I find these flower vases that are easy to find at thrift stores because for several years Walmart sold their Valentine's flowers in these vases. So they show up in thrift stores for $2, $3, $4 a lot of the time. If you draw a triangle on a hyperbolic vase like this and measure the angles of a triangle using a curved protractor. I print out protractors on laser transparencies. You can find a significant deficit in the angles due to that curvature, as low as 160 degrees when you add up the angles of a large triangle drawn on that surface. So students can understand the difference between positive versus negative curvature. And they can also understand that certain surfaces that we would regard as curved in the colloquial meaning of the word, like a cone or a cylinder, actually are not curved in this precise mathematical sense that we mean in general relativity. In other words, if you draw a triangle or a circle on a cylinder or a cone, you can do so without distortion, and all the rules of Euclidean geometry apply. Another important idea in general relativity is the idea of a geodesic, or a path that an object follows through space-time. Again, this can be looked at by analogy by looking at paths on a globe and comparing them to an equivalent path on a flat map that parameterizes that space in a different way. So with some string and some curved rulers, students can draw a path between 2 cities on a globe and then transfer that path by using landmarks on land from the curved surface of the globe to the quote-unquote flat map, and they can see that that shortest distance between 2 points on a globe does not correspond to the shortest distance that you would obtain with a ruler on the flat map. And you can have a discussion with students or ask them to speculate about which path is the shortest, which path is the straightest, and how we define straight within a curved coordinate system like the latitude and longitude system, say, that we apply to the surface of the Earth. When it comes to cosmology, I always do with all my astronomy classes a activity where they examine the expansion of the universe by analogy of just some galaxies drawn on a piece of paper that are then photocopied at 120%, 140%, 160%, all the way up to about 200%. And they measure the distances between those galaxies, and they graph how much farther they get apart over time. And if they do this carefully, you obtain a linear relationship that is analogous to Hubble's law for the expanding universe. You can measure the quote-unquote speed of those galaxies, in other words, how much the distance between them changes per copy. And you can actually extrapolate backwards to figure out how many copies ago the virtual Big Bang would have happened in this photocopier universe. Later on in the semester, when we're talking about dark matter and dark energy, we do the lab again, although this time I give each group of students a different photocopied universe. Some photocopied at an accelerating rate, say 110%, 130%, 160%, and other groups I give a universe that is photocopied at a decreasing rate, say 120%, 130%, 135%, 137%. So some of the students will be measuring an accelerating universe and some will be measuring a decelerating universe. And what they'll see is that the relationship that they get for velocity as a function of a distance is no longer linear, and that they can deduce from that that their universe is accelerating or decelerating, and then they can speculate about how this would cause you to either underestimate or overestimate the universe if you had assumed that the expansion of that universe was constant. Lastly, I do an activity with my students where they are asked to explore the early universe using the cosmological models that are built into Wolfram Alpha. If you only use Wolfram Alpha as a calculator, you're missing a lot of stuff that's hiding in there. For example, you can type in something like 1,000 years after the Big Bang, and Wolfram Alpha will tell you all this information about what was going on in the universe there, including the fraction of the current radius of the universe that the universe was at that time, and the temperature of the universe at that point in time, and whether or not during that epoch the universe was radiation dominated, matter dominated, or dark energy dominated. And you can have students make a graph of, say, the temperature over time and radius over time and talk about whether these things are linear or something else. And you can ask students to pinpoint by typing different numbers into the search bar where exactly this transition happens, such as the transition from a radiation-dominated universe to a matter-dominated universe that happens at recombination. If you're interested in any examples of these activities with the student questions, feel free to email me at dmorgan@gmail.com, and I will do my best to share those things with you if you're interested.